Welcome to the Nexus. Today we go back to my roots in aviation. There seems to be this idea that jet engines don't run on fuel but on some form of compressed air. Let's see if I can help correct some misunderstandings on that. So today's period of instruction is a result of a lengthy conversation with Jones senoJ, and yes, I'm pretty sure I'm mispronouncing that, in the comments on a couple of his videos. I don't have much of an opportunity to cover aviation related subjects, which is actually my specialty. Channel regulars will probably know that I used to work in aviation when I was an active duty Marine. Now, there are a couple of conspiracies out there concerning aircraft, and they stem from a misunderstanding of how an aircraft actually works. The most prevalent one I've seen thus far is this idea that engines don't use fuel. Jet engines don't use fuel. This is a result of not realizing how much fuel can be stored in an aircraft, where it is stored, and a misunderstanding of how jet engines work, all of which we'll be covering, and all of which are easily addressed. Watching a few of Jones's videos, he seems to have issue with the use of diagrams and manuals to explain these things, so where possible, I will be using footage of what I'm talking about. There are a couple of places where that will neither be practical or possible, and I will explain why at those points. Let's start with the fuel system itself. The 777 series has a couple of variants, with the 200ER version having a large central tank, while the standard 200 version replaces one central tank with two on either side of the main fuselage. This leaves what is called a dry bay, which can be used for cargo space. Both tanks will be connected by cross-feed pumps and valves, which we'll be getting to in a moment. For the sake of simplicity, we will be focusing on the standard 200ER or extended range variant. Now, as you can see here, the fuel cells are arranged in such a way that they each hold right around 50,000 liters, or nearly 14,000 gallons each. They are also positioned this way to properly balance the aircraft's center of gravity. This is done with those cross-feed pumps and valves that I mentioned earlier, which are operated via computer to shift fuel from tank to maintain balance, but can be done manually if need be. Now, before we get to footage of fueling and of the fuel cells themselves, Jones asked if there was any footage of fuel sloshing around in the tank. Obtaining such footage is both impractical and dangerous. If the cell has a camera in it and is set up in such a way that the cell is adequately lit to film this, it would involve the aircraft being in flight. There is a concerted effort made to prevent objects from rattling around anywhere inside an aircraft. If a camera were to break loose and clog a line, that would become very dangerous, especially if it was a feed line to an engine. You will not find anyone willing to allow such a thing on their aircraft. It is simply too risky. The sloshing is prevented or minimized in a couple of ways. Extremely porous foam is put into sections of the cells to arrest that kind of thing in helicopters, to prevent all that heavy liquid from jostling around. I misspoke in one of your comment threads on this when I assumed it would be a similar setup in fixed-wing aircraft, but that was an error on my part, as I discovered on further research. However, there are surge tanks which rob the fuel of its momentum and then drain it back into the main tanks, and the angle of the wings makes the orientation of the tanks less conducive to the effects of a wave, so to speak. Since commercial airliners aren't as maneuverable as, say, a fighter jet, the surge tank takes care of what the tank orientation cannot. Add to that the fact that the cells are divided from one another, like you see here, and any shift in weight is realistically minimal. Now, since my specialty is specifically in helicopters, I also misspoke in one of our interactions on the fuel cells on a static display aircraft having the cells removed. In some helicopters, this is the case because the cell is essentially a carbon fiber bag manufactured to sit in an area around the main drive transmission, with some having further cells underneath the cabin floor. This is model dependent, of course. In fixed-wing aircraft, the cells are solid and manufactured from aircraft-grade aluminum and further compartmentalized by stiff walls. not for the claustrophobic to be sure. The lines we see here serve transfer purposes, like we talked about earlier, and in the main feed tanks, there are some lines that go directly to the engines. So let's go back out and look at a fueling real quickly. I borrowed a clip from fellow mech Ian Obi-Wan for this. The wing is a different temperature than the fuel. As you can see, when the fuel is pumped in, the skin of the wing changes temperature. There's a fuel manifold system that divides up the fuel to be sent to all cells, to my knowledge, pretty much simultaneously. So it isn't really a surprise that you can't hear it fueling because the wings are almost never empty and the fuel is pumped into the cell from the bottom, so that will further reduce the noise. Commercial airliners can, to the best of my knowledge, only be pressure fueled, but helicopters have a gravity fill option like you would use in your car. You have to watch it though because it won't automatically shut off. So there is fuel going into the aircraft and being distributed throughout the wing to individual tanks connected to each other by cross-feed and overflow lines to facilitate transfer as needed. So let's move on to the power plant. The engines on the 77 series airframes come from a few manufacturers, but for uniform performance, they will all be from the same manufacturer for any one aircraft. One may have Rolls-Royce engines, and another may have engines from GE, but they will not mix and match as a general rule. Now, Jones gave an almost adequate explanation of how a jet engine works, but there are a couple of points that need to be cleared up, so let's go through it. Any engine can be divided into 4 stages: intake, compression, combustion, and exhaust. There are several different types of jet engine, with the only thing different between them being how they transfer the energy that is generated. Commercial airliners use turbofan, while helicopters use a turboshaft. A turbofan engine draws in air into the core at first during startup, which starts with an intake section and then feeds into the compressor stage, which squeezes the air down and heats it up in the process until it reaches the combustion chamber, which is affectionately known as the can. Up to this point, Jones was on track and giving a passable description of how it works, including a description of pneumatic air from the APU driving the starter in the engine. However, while the APU is small enough to start with a battery, it is not constantly powered by the battery. It functions the same way that the main engine does, just on a small scale, powering a generator for electrical power, and on smaller aircraft providing limited hydraulic function, enough to center the controls. But back to the can. There is not a constant stream of fuel coming from several pencil-sized holes. The nozzle forces it out as a fine mist, like you see here. Now, I know this looks like a lot of fuel, and it is, but there are a few things I need you to bear in mind here. First of all, the thin mist you see here is what is known as the primary flow. It's used in startup to prevent the igniters from trying to light a mixture that is too rich, meaning there is not enough O2 for it to be ignited. Once it is burning, however, the secondary higher flow takes over. The rate of flow that you see here is rarely used. This is around the upper operational limit for this particular nozzle. See, engine speed and torque values are measured in percentage of operational norms, meaning that 100% engine speed is the high end of normal operational limits. What you're seeing here from this nozzle would be well beyond normal operational limits, up to right around 125% of engine speed. This leeway exists for things like emergency power, which is why you will almost never see this kind of flow. Realistically, it would be about 3/4 of this, maybe a little bit more. So that constant flow of fuel keeps sustaining the burn, while air being drawn in from the front forces the combusted and expanding gases out the back through a series of turbine blades, which drives a shaft leading to the intake fans, including the big one at the front. This will continue until fuel flow is interrupted. Remember that there is quite a bit of fuel in an aircraft, and remember the cruising speed is about 0.8 Mach, right around 600 miles an hour. So normal operation at 100% engine RPM means you will cover a considerable distance with the fuel on board. Now, this is another area where filming the combustion inside the can is impossible. But on the small scale, you can see it pretty clearly is burning fuel. This jet the hacksmith bought went through a couple of gallons quickly all on its own and does some serious damage to things put in the way of the exhaust. Now, to showcase the fact that the engines are burning fuel and that the exhaust is extremely hot, we are going to talk about hot starts. Plumes of mist coming out of the engine on a warm day isn't condensed water. That is fuel and is something that is definitely not normal. It results in what is known as a hot start. That happens either because the fuel was introduced too early in the startup process or the engine has difficulty getting up to speed due to a weak starter. Both situations result in poor airflow, and if it's bad enough, it means that the engine needs to be shut down to prevent the temperature from getting too high in the can and damaging the engine. There was also a concern on Jones' part about moisture getting into the engine. Remember that while the engine is turning on a turbofan, about 90% of the air is going straight through his thrust, bypassing the core entirely. Rain and cloud vapor won't do a whole lot to slow the engine down because most of it doesn't make it into the core. Even in extremely humid environments, the performance effect of moisture is negligible. So now that we have covered that fuel is stored in the wings, that it can take on the load per specifications with no trouble, that sloshing of fuel is arrested by design of the cells, and that jet engines do indeed burn fuel, we need to cover why burning fuel is necessary. Yes, if you wanted to, you could conceivably make an engine that would function like a jet by forcing compressed air through a turbine. However, it will run out of energy very quickly, and the laws of physics and thermodynamics mean you don't get anything for free. Without constant force being applied to the turbines to overcome air resistance and friction that is still present despite well-lubricated bearings, the energy driving the fan will eventually peter out and it will stop. What you then will have is a massive hunk of metal that is catching air and not doing anything useful with it. That means a lot of drag. And on twin engine aircraft, not only do you have to compensate for the plane pulling towards the non-functional engine, you also have to work harder to maintain or gain altitude. And depending on your weight, gaining altitude probably won't happen. See, you don't lose 50% of your thrust capability in this case. Because of the added drag, you lose around 80% of your total thrust capacity on a twin engine aircraft. We use fuel because it imparts more force to the turbine from the expanding gases than simple compressed air can provide at any temperature. The only other option Jones may consider viable is essentially a perpetual motion machine, which would violate the first or second laws of thermodynamics, or both. Like I said, you can't get anything for free.